Polynomial regression is a statistical tool, and what we do in our domain is instead of creating a regression line, a predicted line, we predict a surface. In other words, I told you about the IDW, inverse distance weighted analysis. There I said the predicted surface will follow through all the data points. A data point in a map is a geospatial data point because you have latitude values and longitude values for every data point. Then you will have a feature, for example, CED. CED location, CED is a feature, CED has got attributes, and CED's location is defined by a latitude and a longitude value. That is what is called a geospatial data. That is what geospatiality is all about, location specific. The science of where you are, that is what is GIS. The science of where you are located, that is what is GIS. Now, for example, you take Thiruvananthapuram district. Let us assume that right from the foothills of the Western Ghats in the Thiruvananthapuram district, we have several air quality monitoring stations. Now, several in the sense, let us say, 10 or 12, because we are only 300, somewhere around 3,000 square kilometers of area. When you have 10 stations, that means in that area, you are addressing 300 kilometers square per station. That's enough. We don't have even that. That is a point. Anyway, if we have that kind of distribution as far as data regarding air quality is concerned, well, you wanted to take a closer look at what happens to the particulate matter 2.5, PM 2.5 as it is called, very dangerous thing. If you are inhaling at your age, well, in another 10 years you will get asthmatic or some kind of lung disease it can cause. If you are a child, then the story is still different. In India, there are at least 10,000 people dying every year out of inhalation of this 2.5. 2.5 means 2.5 PM, particulate matter 2.5. There is a particulate matter 10. Particulate matter 10 is, it only will attach your shirt and your skin. Whereas this 2.5 thing, this will get into the bloodstream, go to the lung, to the heart, to the brain even. So, if you want to map that, you have a tabulated data available. Well, it will not give you, even if you have a trained mind, a quick picture of whether on a certain date, on a certain year, on a certain month, which way PM 2.5 was varying, from higher value to lower value or lower value to higher value, because if it is provided in a tabulation, whereas if it is given in a map, you will have some idea. But still it is not very clear, even for the trained mind. You will say, here is a higher value. That's it. Whereas, when you create a first degree, as it is called, polynomial regression or a trend surface, polynomial trend surface, it is actually a raster surface. Our data input is, what is it? Location based. Now it is a raster, the so-called trend surface. That raster data surface will have an orientation decided by the numerical data, the numbers corresponding to the monitoring stations, 10 of them distributed in the Trivandrum district. Well, this surface, predicted surface, will not contain all the numbers on the surface. It may have one or none on the surface, on the predicted surface. When you have none, those points will be closer to either above the predicted surface or below the predicted surface. Suppose you have some sitting on the predicted surface, then the rest of them will be either above the surface that was predicted by the analysis or below it. See, because it is below and above that kind of location, each data point in the XY, not in the XY chart, in the X1, in other words, our elevation or our PM 2.5, that number is a Z value. You have a X1 and a X2 as the coordinates to define the geospatiality. Then the numbers that are above will have a positive difference. You have a value for the surface at each corresponding to each point. Either the point will sit on the surface or will be above it, then there is a difference from the predicted and the real, or it will lie below the predicted surface, then it will have a value which is less than the predicted surface. This is called residual, the difference. So whatever point that are below the surface that is predicted, they carry a sign, a minus sign. All those points that are on the surface, they don't have. You don't worry about them now because the surface has defined it. Whatever point that is above, those points will carry a sign of positivity. Now, now it is a point that time we have to bring back what is called the root mean square. Root RMS square. That is probably the first thing you learned in the lab during georeferencing. Root mean square. In other words, in order you square all the residuals of the trend analysis. Positive times positive is positive. Negative times negative is positive, right? So you square it in order to eliminate the negative sign. Then, what is it? Root mean square. Then you get the mean, all are positive, mean value, and then square it. So the very same principle, the predicted line is actually with a low root mean square value for the corresponding data values. Low root mean square value. That is low. What is one of the conditions in georeferencing? If looking up, doing that process is in order to achieve or attain the lowest root mean square value. This very same principle is applied here, applicable here. This particular first degree trend surface it is called because it is always a plane, like a sheet of paper. Then there is a second degree trend surface you can create, which will be like for example, in Tiruvandhuram district where we have the 10 stations for PM 2.5 reporting. There are surface, what is the real ground surface? There are valleys, there are hills, right? So keep in mind that when you create a first degree surface, polynomial trend surface. It will not show, it will not reflect the valleys or hills. Well, when you have the next step, or instead of first degree, if you go to second degree, you will not contain all the valleys or all the hills, but there will be a general distribution. If your valleys are much more than the hills, then it will be a trough. Like as if you had bent the paper downward. Or you can have a similar situation. The second degree surface will show a up-bended surface, bended upward. Then the third, what is the advantage then? Your number of, your residuals, positive residuals, negative residuals, that magnitude will decrease. There will be more of the data points contained in the surface predicted than in the previous case, in the first degree. And, as a convention, you go to the third degree surface only, third degree polynomial trend surface. Then, practically, large number of points will be contained within the third degree surface. The appearance of the surface will be either a upbend followed by a low downbend, or initially a downbend followed by an upbend. So, this is what trend surface analysis or polynomial trend analysis is based on. It is a very useful. We always go for calculating the first degree trend surface because it gives us a picture of which way a certain attribute measured, a water quality maybe, a potassium content in the soil maybe, or anything you can imagine of. Any measurement you have made on a geospatial basis. And that will give you a picture of which way the particular mapped variable or attribute is decreasing, increasing, etc. If there is no decrease or increase, you don't have to do the first degree trend analysis or under geostatistics. There are two more tools under geostatistics. The one is called a spline, the other is called the kriging. Well, let us at least study about how to make IDW and the polynomial trend. Well, that's all I have to tell you this afternoon. Bye, and enjoy the labs. Okay, thank you.